Every summer, bathers are caught by surprise by rip currents. That can quickly lead them into deeper water, where a combination of exhaustion and panic too often results in a drowning death. Each year, hundreds of people drown and tens of thousands more are rescued from rip currents globally, and it is now well established that they are the primary physical hazard facing recreational bathers on surf beaches worldwide. But what do we really know about these currents? In 2016, an international team of scientists conducted an in-depth study and developed a robust rip current type classification system. The study also provides valuable insights that can help us analyze the mechanics of these currents, understand how they form, and identify the best strategies to escape them, considering different flow regimes. What creates a rip current? When a wave approaches the shore, it starts to break as the water becomes shallower, typically at a depth of about 1.3 times the wave's height. This breaking releases a burst of energy, creating what we call onshore flow. It flows back out through the path of least resistance, often where waves break less. These return flows gather into narrow channels called feeder currents, which merge into the rip neck, a fast-moving jet that pulls water, sand, and swimmers offshore. Add the effect of the vortex, the spinning force created at the crest of a breaking wave, and the rip becomes even more powerful. How to spot a rip current? Look for these signs: fewer breaking waves, a darker patch of water, a rippling surface, or floating debris being pulled away behind the surf. Why do rip currents vary? The whole system is shaped by three main factors: wave breaking, the shape of the seabed and shoreline, morphology, and tidal changes. Together they create a constantly shifting zone of water flow. And that's why there isn't just one type of rip current. Each type is driven by different combinations of these forces. Let's break them down. The study identifies and grouped them into three main categories. Hydrodynamically controlled rips. These rips are short-lived and change location quickly. They form on beaches with uniform shorelines and are driven mostly by wave and current interactions. Shear instability rips are triggered by strong longshore currents that become unstable. Flash rips, on the other hand, appear suddenly when these currents are weak or absent, forming eddies that pulse water offshore. Bathymetrically controlled rips. These rips tend to form at consistent spots, guided by variations in underwater topography. Channel rips develop in deeper troughs where waves break less. Focused rips occur where offshore sandbars or reefs bend the waves, concentrating their energy at specific points along the coast. Boundary-controlled rips. These form next to hard edges like headlands, jetties, or rocks. Shadow rips happen on the sheltered side of the structure, where fewer waves break. Deflection rips appear on the opposite side, created by currents bouncing off the boundary. But in many cases, some rip currents are hybrids, driven by several forces at once. Channel flash rips form where small underwater channels interact with shifting currents. Focus channel rips combine bathymetric features with variable wave breaking. Boundary channel rips form where solid structures have carved a permanent trench, blending topography and current deflection. Embayed cellular rips. Finally, on pocket beaches enclosed by headlands, large looping rip currents, known as cellular rips, dominate the entire embayment. Their formation is shaped by the bay's width, wave direction, and boundary effects, and they can grow especially strong during storms. This study gives us solid scientific insight that complements our field experience. With it, we can better anticipate ocean behavior and raise awareness about potential dangers. But prevention doesn't stop with us. If this video helped you, share it with your friends, colleagues, and anyone who might benefit. Every informed person is a step towards safer beaches for everyone.